Hello, let's look at number 9. Okay, so a block of mass m1 equals 2 kg moves towards block m2, which is attached to a light spring. The second end of the spring is fixed to the wall. The graph below shows the velocity of the block m1 as a function of time before and after the collision. Before the collision, block m1 moves with a velocity of 4 meters per second, and after the inelastic collision, the velocity drops down to 2 meters per second. Calculate the mass of block m2. Okay. Oops. Let me go ahead and change that. Okay, so we're looking at A. So calculate the block of M2. So they are going to collide inelastically. So let's go ahead and just start with our momentum. The reason I know this is a momentum problem is because it has momentum, right? So obviously we have this collision, but they've also given us enough information, right? They gave us the velocity before and after. And remember, there's nothing wrong with setting something up and then realizing you don't have enough information and you maybe need to try something else or look at a different thing, okay? But let's go ahead and try this. So we have one object moving at the beginning, so that will be mvi equals, they collide and stick together, so it'll be m plus m vf. And they tell us both of the velocities. So it starts at 4 and drops to 2. So I have my initial mass is 2. So I have 2 times 4 equals 2 plus m times 2. Okay, so I have 8 equals 2 plus m times 2. So divide by 2, that cancels. Left with 4 equals 2 plus m, so m equals 2 kg. Okay, so the mass of that second block, m2, is just 2 kg. Okay, and so that would be the answer there. Let's go ahead and look at part B. So part A was sort of just a more simple momentum question, not too bad, just inelastic. But part B and C are definitely more tricky, difficult questions, okay? So let's go ahead and look at part B. So it says, after the collision, the two blocks move with a velocity given by the function v equals 4e to the 8t. So v as a function of t equals 4e to the negative 8t. Okay, and then it says, find the stopping distance. So I'm just going to kind of graph this. So I have velocity, I have time, and my function is going to look something like this. Okay? And it's saying find the stopping distance. Now, you know that the area under the curve, okay, so the area under this curve is what? I have a velocity time graph. What's the area under the curve? The area is distance. Okay? Now, normally we just think, okay, distance, we're approaching infinity here, right? So this velocity is never truly reaching 0. But because it is approaching 0, there's actually a finite distance here. So if we can find this area here, it will actually tell us the distance that it travels when it ends up actually stopping, okay? So it looks like a very difficult question, but it's not as bad as it looks, okay? Now, remember, if I want to find that area, I need to go from 0 to infinity and take the integral of that function, okay? So my distance, d, is equal to the integral of vt dt, but I want to go from 0 to infinity. The reason I want to go to infinity is because since this is an asymptote here where this graph is approaching 0, it never truly gets to 0 until it gets to infinity. So I want to go all the way to infinity. Now, in real life, in practice, it eventually actually stops, but mathematically, we can just show that it is still getting a little bit closer to 0. That velocity is getting a little bit closer, okay? And so this is just going to be an antiderivative, okay? So I have the integral from 0 to infinity of 4e to the negative 8t dt. Okay, so now I need to take my antiderivative. And so remember, the antiderivative of e to the t is just e to the t. Okay, but if I have a number here, then it's sort of very similar where I need that the opposite here, okay? So it's actually very similar to sort of the antiderivative power rule, where I have that 1 over something. So let me go ahead and put that 8 there. So for this, I'll just have 4 divided by negative 8, e to the negative 8t. Okay? And then I'm going to evaluate from 0 to infinity. Now, it feels very difficult. It's like, oh no, I'm approaching infinity. That seems weird. But it's not as bad as you think, okay? If I plug infinity here, e to the negative infinity is just approaching 0, okay? So this equals 4, negative 8, e to the negative infinity, times 8, but 8 times infinity is still infinity, minus 4, 8, e, and then this is just 0. So 8 times 0, okay? So this one here, it's kind of thinking of it as approaching a limit, right? And so as we approach infinity, we get 4, 8 times 0. And so that part is just going to end up equaling 0. And then here we have e to the 0 is just a 1, right? And so this will just equal, this all goes to 0, so negative negative is just 1/2, okay? And so the distance here is just going to be 1/2 meter. Now, I realize it's something we haven't necessarily done a whole lot before, but it's not as hard as it looks, really. It's just taking that antiderivative. Actually, if you look at the formula sheet, a lot of these identities or these formulas here are actually on the formula sheet. So if you ever forget that, you can actually go ahead and look that up and see what it says to help remind yourself. Okay. Now let's go ahead and look at part C. I'll see you in 1 minute.